In this podcast, we're going to go over the physical properties of carboxylic acids, and we'll pay special attention to the structure and how that contributes to those physical properties. All right, so let's take a look at the structure of a carboxylic acid. By definition alone, if we're talking about a Bronsted-Lowry acid, we're talking about a molecule that will donate a proton. So carboxylic acids are no different. They will donate the proton on the OH group. So in that sense, they are acting as acids. They do have a polar carbonyl group with a net dipole. So the carbonyl has a net dipole with your oxygen being slightly negative and your carbon being slightly positive. But also, in addition to that, we also have a hydroxyl group, which is going to give us a slight negative on the oxygen and a slight positive. So we have a net dipole there as well. So what happens when you have multiple carboxylic acid molecules together is they create what's called a dimer. And that's the image that you're seeing right here. So the hydroxyl group interacts with the carbonyl group. And so we have a slight negative charge on the carbonyl and a slight positive charge on the H involved in the hydroxyl group. We create a hydrogen bond there because of that. And the same thing goes for that second part. So the reason why these guys have higher melting points and boiling points than, say, an alcohol alone is because they have two different hydrogen bonds holding them together. That's going to require more energy to separate those forces and to change state. Whereas an alcohol group only has one opportunity for hydrogen bonding. If we were to look at an alcohol. So you only have one opportunity here for that hydrogen bonding, whereas those carboxylic acids have two. Because the presence of two dipoles in our carboxylic acids tend to be more soluble than alcohols, which only have one or have one hydrogen bond. The solubility, as with every organic compound, is going to decrease as the chain length increases. Let's look at a table of comparison for our solubilities as well as our boiling points. So carboxylic acids, because they have the potential to have two different hydrogen bonds with each other, that is a stronger force holding those two molecules together, they're going to have a higher boiling point than alcohols. Same thing with solubility in water. They're going to be more soluble than alcohol in water. Alcohols are more soluble and have a higher boiling point than aldehydes, ketones, and esters. We haven't talked about esters yet, but you can imagine just from the structure alone, notice that they are lacking that OH group on the ends. They're going to be less soluble than the alcohols because of that they don't have hydrogen bonding. Hydrocarbons, of course, are just chain lengths of carbons and hydrogens, which are nonpolar. Those are going to be your lowest boiling point and your most insoluble in water. And again, as chain length increases, the water becomes less likely to surround the entire molecule, and therefore that molecule becomes insoluble in the water, and it forms a layer separate from the water because of that. And we see that a lot in lab. All right, low molecular weight carboxylic acids are liquids at room temperature. If you think back to our discussion on saturated versus unsaturated fatty acids, we never really paid much attention to the name or to the functional group on the end, but they have a carboxylic acid as part of their chain. These are liquids at room temperature if they're unsaturated or if they're a short chain length, but as that molecular weight increases or the number of carbons increases, they become wax-like solids. So a saturated fatty acid, say like stearic acid, that's going to be more solid or more of that lard consistency or a wax-like solid at room temperature versus an unsaturated fatty acid, which is going to be liquid at room temperature. But again, that also corresponds to the number of carbons in the carboxylic acid, not just the level of saturation. Or unsaturation, I should say. Carboxylic acids with long chains is what we're seeing here are called fatty acids, and we're talking 12 to 20 carbons is when we start to classify them as fatty acids. We do see carboxylic acids a lot in nature. Typically, they're not the best smells. Hexanoic acid, which is a 6-carbon 3, 4, 5, 6. Hexanoic acid is the foul odor that's associated with locker rooms and dirty socks. Also, hexanoic acid is what's responsible for giving Limburger cheese its characteristic smell and odor. And if you haven't had a chance to try Limburger cheese, I strongly encourage you to do so. It smells horrid, but tastes delicious. You ought to try it. All right, let's talk about aspirin. Aspirin is also known as acetylsalicylic acid. And acetylsalicylic acid, and you are seeing that structure right here, that first structure, is not actually found in nature. It has to be synthesized in the lab. And it is an analgesic, an antipyretic, so a fever reducer, as well as an anti-inflammatory. So it's kind of a miracle drug. It's one of the first antipyretics that we discovered. Acetylsalicylic acid comes from salicin, which is isolated from willow bark. So this is a naturally occurring compound. So back in the day, if you had a headache or you had any other issues, you would have to take one form of this, either salicylic acid or you'd have to take sodium salicylate. Each of these had their own issues. Salicylic acid, because it's an acid, it tended to irritate the mucus lining of your stomach, okay, producing ulcers and unwanted side effects. So it was one of those, do I really have that bad of a headache, to put up with an irritation of the mucous membrane, not only of the stomach, but also of the mouth. Sodium salicylate was another form of salicin, and the problem with sodium salicylate is that it's incredibly sweet. It's almost too sweet for most patients to be able to take that. So Felix Hoffmann was a chemist who worked for Bayer, and he was able to take salicin and create another form of salicin, another form of aspirin, acetylsalicylic acid. And modern day aspirin was born. Acetylsalicylic acid doesn't have any of the undesired side effects that you see in salicylic acid and sodium salicylate. So it's not super sweet, and it doesn't irritate those mucous membranes of the mouth or the stomach. Felix Hoffmann was motivated by personal reasons to do this. His father suffered from rheumatoid arthritis and truly could not tolerate the sweet taste of sodium salicylate. So his son set off and discovered what is modern day aspirin for the Bayer company.